You shed skin. Every day, little flakes of you come off and float around the room and settle on the bookshelf and pile up behind the couch. Somewhere along the way, somebody told you that the dust in your house is mostly you. Mostly dead skin cells. 80%, some people say. 70%. Whatever the number, the picture is clear. You're living inside a cloud of yourself. And I have to tell you, I believed this for a while. It sounds reasonable. A human being drops about 1.5 grams of dead skin a day. Over a year, that's more than 1 pound. You've got family members, you've got pets, you've got visitors. All of them shedding. And where does it go? Into the air, onto the furniture, into the carpet fibers. Dust. That's you floating around. Right? Wrong. That's completely wrong. And I can prove it. Not because shedding skin is a myth. You do shed skin. That part is real. The wrong part is the leap from you shed skin to therefore your house dust is mostly dead skin. Because when you actually go and collect dust from a home, when you take it to a lab and put it under a microscope and run the chemistry, the story falls apart. The dust in your house is one of the strangest, most complicated mixtures of matter you will ever encounter, and dead skin is only a fraction of it. So what is it really? That's what I want to talk about. And the answer is going to take us places you wouldn't expect. Because dust, it turns out, is not boring. Dust is a museum of everything that has ever passed through your life. And some of it came from space, literal outer space. Let me start with the wrong idea, though, because I think it's important to understand why it's so convincing. You've heard the number. 80% dead skin, or 70%, depending on who's telling you. It shows up in magazines, in documentaries, in books about biology. Somebody with a degree says it on television, and suddenly it's a fact. The reasoning feels airtight. Humans shed, dust accumulates. Therefore, dust equals shed. Humans. But this is what we call a plausibility argument. And in science, plausibility arguments are dangerous. They feel true. They sound true. But they skip the part where you actually go and check. The number came from, as far as anyone can trace it, some informal estimates that were never really rigorously measured. It became a kind of folk fact, the sort of thing that gets repeated so often that nobody thinks to question it. And here is why it matters to question it. Although, when you do the real experiment, when you gather dust from dozens of homes and actually analyze it, the dead skin fraction is significant, but it's nowhere near 80%. It varies wildly. In some homes it's maybe 20%, in others maybe 50%. But the average is much lower than the popular claim. And the remaining fraction, the majority in many cases, that's where things get truly interesting. Why did the wrong number stick so well? I think there are 2 reasons. The first is that it's vivid. Dead skin. Gross. Memorable. The human brain latches onto things that are disgusting and personal, because disgust evolved to protect us from contamination. A fact about dead skin cells triggers your disgust response. And disgusting things are sticky in memory. The second reason is that nobody has a competing story. If I tell you dust is a heterogeneous mixture of organic and inorganic particulate matter from diverse anthropogenic and natural sources, which is what a scientist would actually say, your eyes glaze over. Dead skin is a story. Heterogeneous particulate matter is a sleeping pill. So the wrong but vivid story wins. This is a general problem in science communication, and it drives me a little crazy. The truth about dust is far more interesting than the myth. But the truth is complicated, and complicated doesn't fit on a bumper sticker. So we get the bumper sticker version, and we lose the wonder. Let me give you the wonder back. Let me walk you through what's actually in that dust, piece by piece. First, textile fibers. This is one of the biggest contributors, and it rarely gets mentioned. Every time you sit on a couch, the fabric releases tiny threads. Every time you fold laundry, every time you pull a sweater over your head, cotton sheds, polyester sheds, wool sheds, your curtains shed, your bedsheets shed. These microscopic threads break off, drift through the air, and settle onto every surface. In many homes, textile fibers are the single largest component of dust by mass, not skin, fabric. Think about that for a moment. You are breathing in tiny fragments of your own clothing all day long. The shirt you wore last Tuesday, few molecules of it are still floating around the living room. And there's a modern twist to this. A lot of your clothing is made of synthetic materials, polyester, nylon, acrylic. When those fabrics shed fibers, they don't biodegrade. They persist. They break down into smaller and smaller fragments, but they don't disappear. You've heard about microplastics in the ocean. Well, there are microplastics in your dust. Tiny threads of synthetic fabric, fragments of plastic from packaging and containers, particles shed from nonstick coatings. Your house is full of plastic dust. The EPA and various environmental researchers have documented this extensively. When you dust your shelf, you are handling a sample that contains plastic. Not a lot, not enough to see, but they're accumulated, persistent, and increasingly a subject of medical concern. There's something almost eerie about this. Plastic was invented to last. We engineered it to resist degradation, and it does resist magnificently. But in the process of resisting, it sheds tiny fragments of itself into the air around us, and those fragments, because they're designed to last, hang around in our dust and in our lungs for a very long time. We built a material to defeat entropy, and entropy found a loophole. Second contributor, soil particles. This one surprises people, but think about your shoes. You walk outside, you step on dirt, you track it back in. The soles of your shoes carry mineral grains, silicate particles, tiny fragments of rock. Even if you take your shoes off at the door, the particles that were already on you, on the bottom of your socks, on the dog's paws, on your children's knees, those get distributed through the house. In some studies, soil and mineral particles make up a quarter or more of the total dust mass. That's rock. Ground up earth. Your living room has actual geology in it. And this is where it starts to get strange. Those soil particles don't just sit there being inert. They act like tiny sponges. Environmental chemists have discovered that particles from outdoor soil, once they're inside your house, begin absorbing chemicals from the air. Your furniture gives off compounds. Your carpet gives off compounds. The paint on your walls, the plastic in your electronics, the flame retardants in your mattress, they all slowly release molecules into the indoor air. And those molecules land on dust particles and stick. The dust becomes a collector, a chemical reservoir. It accumulates things. Researchers at Duke University and the University of California, Berkeley, have analyzed household dust and found hundreds of chemicals in it: flame retardants, plasticizers called phthalates, pesticides, polycyclic aromatic hydrocarbons, which come from cooking and combustion, chlorinated paraffins from industrial products, nonylphenol phenol ethoxylates from detergents. And those are just the ones we know how to detect with current instruments. An environmental chemist named Miriam Diamond at the University of Toronto made a point that I find very striking. She said that dust in a house accumulates year over year. Even if you clean regularly, it gets entrenched in your carpets, in the crevices of your floors, in the gaps between floorboards. A house that was built decades ago might still have dust containing traces of chemicals that were banned long before you moved in. DDT, for instance, was banned in the early 1970s in the United States. But in old houses, traces of it still appear in the dust. The house remembers, the dust remembers. So let me update your mental picture. Dust is not a cloud of dead-you. Dust is a cloud of fabric, threads, ground-up rock, chemical residues from your furniture, traces of banned pesticides, and yes, some dead skin mixed in. But we're not done. Pollen. If you have windows, if you have doors, if you have any ventilation at all, pollen grains drift in. Ragweed, grass, tree pollen, tiny yellow specks of reproductive material from plants just floating around your kitchen. In spring and summer, the pollen fraction of household dust goes up noticeably. You can see it sometimes, a faint yellow film on a windowsill. That's plant sex, right there on your windowsill. Pet dander. If you have a dog or a cat, they're doing the same thing you are, shedding tiny flakes of skin and hair. But pet dander is chemically different from human skin. But the proteins in it are what trigger allergic reactions. And pet dander is remarkably persistent and mobile. Studies have found cat allergens in buildings where no cat has ever been because people carry the particles on their clothing and transfer them to chairs and carpets. Your coworker's cat is in your dust. Insect fragments. I know this one is unpleasant, but it's real. The exoskeletons of tiny insects, pieces of cockroach casings, body parts of dust mites. These are part of your dust too. And dust mites deserve special attention because they connect back to the skin story in a way that's really elegant. Let me tell you about dust mites. A dust mite is a creature about 1/4 of a millimeter long. You cannot see one with your naked eye. It has 8 legs, making it an arachnid, a cousin of spiders and ticks, and it lives in absolutely enormous numbers in your mattress, your pillows, your carpets, and your upholstered furniture. An old mattress can harbor millions of them. What do they eat? Dead skin cells. That's their food. So the skin you shed doesn't just lie there in the dust passively. It gets consumed. The dust mites eat it, digest it, and excrete waste pellets. Each dust mite, over its roughly 80-day lifespan, produces about 1,000 of these allergen-rich waste particles. The mites also shed their own exoskeletons as they grow. So when you breathe in household dust and have an allergic reaction, you're probably not reacting to your own dead skin. You're reacting to dust mite feces. You're reacting to the digested remains of you, processed through the gut of a creature too small to see, excreted and suspended in the air of your bedroom. This is what I love about looking at things carefully. The popular story says dust is dead skin, and that's kind of gross but also kind of boring. The real story says dust is dead skin that has been eaten by invisible arachnids whose fecal matter you inhale at night. That's much worse and much more interesting, and the numbers on dust mites are staggering when you start counting. A single human sheds enough skin in a day, about 1.5 grams, to feed roughly 1 million dust mites. A typical used mattress may contain anywhere from 100,000 to 10 million of them. They breed quickly. A female can add 25 to 30 new mites per week, and each mite produces about 1,000 allergen particles in its lifetime of about 80 days. So a mature mattress is not just a place you sleep. It's a thriving ecosystem, a coral reef of microscopic arachnids grazing on a continuous rain of dead human tissue. You're the food supply, the mattress is the biome. The Dutch scientist Antony van Leeuwenhoek, the man who essentially invented the microscope, first reported seeing these little animals in dust back in 1694. He didn't know what they were, but he saw them, wriggling and scuttling. It took another 270 years before we understood the connection between these creatures and the allergic reactions that affect roughly 10% of the human population and up to 80% of people with allergies. The key insight was this. It's not the mites themselves that you're allergic to. It's the proteins in their waste products and their shed exoskeletons. These proteins are incredibly potent allergens. When they become airborne, which happens every time you roll over in bed or fluff a pillow, they get inhaled. Your immune system mistakes them for a threat, and you get congestion, sneezing, itchy eyes, and in severe cases, asthma attacks. So your nightly tossing and turning is essentially shaking a tree full of allergens directly into the air you breathe. But there's a physics dimension to all of this that I want to dig into, because this is where dust goes from being a household nuisance to being a genuine window into how matter behaves. Let's talk about size. Dust particles range enormously in size. The biggest ones, the ones you can see floating in a sunbeam, are maybe 50 to 100 micrometers across. A micrometer is 1/millionth of a meter, or roughly a 25,000th of an inch. Those visible particles are the boulders of the dust world. Most dust is much smaller. But wait, why can you see those particles at all? 100 micrometers is tiny. Your eye can barely resolve things that small. The answer is light scattering, and it's a beautiful piece of physics in its own right. When a beam of sunlight enters your room through a gap in the curtains, it's usually invisible. You don't see the beam itself, you see the spot on the wall where it lands. But if the air contains dust, suddenly the beam becomes visible. A shaft of golden light, full of sparkling, dancing motes. Why? Because each dust particle scatters some of the light sideways toward your eyes. The particle is too small for you to see its shape, but you can see the flash of light it redirects. You're not seeing the dust particle, you're seeing the light that bounced off it. This is called Tyndall scattering, named after the Irish physicist John Tyndall, who studied it systematically in the 1860s. It's the same reason a car's headlight beams become visible in fog. It's the same reason a laser pointer's beam shows up in a smoky room. Tiny particles in the air redirect light toward you, making the beam visible. And the amount of scattering depends on the particle size relative to the wavelength of light. Visible light has wavelengths between about 400 and 700 nanometers. A dust particle of 50 micrometers is about 100 times larger than the wavelength. At that scale, the scattering is strong and roughly equal across all colors, which is why sunbeam dust looks golden or white, reflecting the color of the sunlight itself. For much smaller particles comparable in size to the wavelength, the scattering starts to favor shorter wavelengths, blues and violets. This is called Rayleigh scattering, and it's the reason the sky is blue. The molecules in the atmosphere are tiny, much smaller than the wavelength of light, and they scatter blue light more than red. So when you see dust in a sunbeam, you're witnessing a physics lesson about light and particle sizes. The biggest particles scatter all colors equally, the smallest ones scatter blue preferentially, and the ones in between do something intermediate. Your sunbeam is a spectrometer. There is something magical about that sunbeam moment, and I mean magical in the way that physics earns it. Every child has stood in a shaft of afternoon light and watched the dust dance. It seems random, it seems purposeless, but every single thing in that image is governed by precise laws. The angle of the light follows Snell's law of refraction as it passes through the window glass. The scattering follows Mie theory for the larger particles and Rayleigh theory for the smaller ones. The dancing follows Brownian statistics driven by the kinetic energy of air molecules, whose speed distribution follows Maxwell and Boltzmann. The settling, or failure to settle, follows Stokes' law modified by the Cunningham correction. Everything you see is a physics textbook written in floating specks. And yet nobody teaches it that way. We teach Brownian motion in a chapter about thermal physics. We teach Stokes' law in a chapter about fluid mechanics. We teach Rayleigh scattering in a chapter about optics. But in a sunbeam, they're all there together, tangled up, inseparable, the way physics actually works in nature. Nature doesn't separate into chapters. Only textbooks do that. Particles below about 10 micrometers are what scientists call PM10. They can penetrate into your lungs. Below 2.5 micrometers, PM2.5, they go deeper, into the tiny air sacs called alveoli, where your blood exchanges oxygen and carbon dioxide. These are the particles that cause the most health damage, and they're completely invisible. You will never see them, you will never know they're there, but they accumulate on every surface, and they float in every room. There's a beautiful question here about why some particles float and others settle. If I drop a baseball, gravity pulls it straight down, fast. If I drop a grain of sand, it still falls pretty quickly. But if I release a particle of dust that's only a few micrometers across, it drifts, it floats, it wanders around the room like it can't make up its mind. Why? Two things are happening. The first is air resistance, which you'd expect. Small particles have a huge surface area relative to their mass. Gravity pulls them down, but the air pushes back, and for very small particles, the air wins for a long time. A 10 micrometer particle falling through still air takes minutes to settle. A 1 micrometer particle can stay aloft for hours. That's just from air resistance. But the second thing is more interesting. The really small particles, a few micrometers and below, are being pushed around by individual air molecules. This is Brownian motion, and it is one of the most beautiful things in all of physics. Let me tell you the story. In 1827, a Scottish botanist named Robert Brown was looking through his microscope at pollen grains suspended in water. He noticed that tiny particles inside the pollen were jiggling, not drifting with a current, not settling, jiggling, randomly, constantly. He tried it with other things, mineral dust, ground up glass, particles from all sorts of sources, same jiggling, living or dead, organic or mineral, it didn't matter. These tiny particles danced. Nobody could explain it for almost 80 years. And then in 1905, a young clerk in a patent office in Switzerland published a paper that did. His name was Albert Einstein, and this paper, not the one on relativity, not the one on the photoelectric effect, this paper on Brownian motion, is what I consider one of his most profound contributions. Here is what Einstein showed. The tiny particles are being bombarded by molecules. Water molecules in Brown's case, air molecules in the case of dust. These molecules are moving fast, hundreds of meters per second, and they're hitting the particle from all sides, but the hits aren't perfectly balanced. At any given instant, a few more molecules hit from the left than from the right, or from above than from below, and the particle lurches. A moment later, the imbalance shifts and it lurches in a different direction. The particle is being kicked around by invisible molecules. And Einstein showed that by measuring the kicking, by tracking how far the particle wanders over time, you can calculate the size of the molecules doing the kicking. You can prove that atoms exist. Now remember, in 1905, atoms were still controversial. Serious scientists debated whether atoms were real physical objects or just convenient mathematical fictions. Ernst Mach, one of the great physicists of the 19th century, thought atoms were nonsense. He said they were mental constructs, useful for calculations, but not actually there. And he wasn't some crank. He had good reasons. Nobody had seen an atom. Nobody had directly measured one. The periodic table worked, sure, but maybe it was just a pattern, not evidence of discrete particles. Einstein took Brownian motion and turned it into a measurement device. He derived a formula. It said if you watch a particle of known size and track how far it wanders from its starting point after a given time, and you know the temperature and viscosity of the fluid it's in, you can calculate a number called Avogadro's number. And Avogadro's number tells you how many molecules are in a given amount of substance. If the number comes out finite and consistent, atoms are real. A few years later, a French physicist named Jean Perrin did exactly this experiment. He made tiny uniform spheres, suspended them in water, watched them wander under microscope, and calculated Avogadro's number. The number came out right. Atoms are real. Perrin won the Nobel Prize for this work in 1926. So let me connect this back. The dancing of dust in a sunbeam is the same phenomenon. Air molecules instead of water molecules, but the physics is identical. Each visible dust particle is being bombarded from all sides by nitrogen and oxygen molecules moving at about 500 meters per second. At any instant, the bombardment is slightly uneven, and the particle lurches. A moment later, a different unevenness, a different lurch. The path is random, unpredictable, and beautiful. Think about that. Dust, floating in a beam of sunlight in your living room, is performing a physics experiment. Every particle is being kicked by air molecules, jiggling and wandering, and the pattern of that wandering is a direct consequence of the molecular nature of matter. The dancing dust is proof of atoms. You can see the evidence with your own eyes, in a sunbeam, in your house, right now. Brownian motion is also why the very smallest dust particles never settle. Gravity says they should fall, but the molecular kicks keep pushing them back up. For particles below about half a micrometer, the kicks win. They stay suspended essentially forever, or until they stick to a surface, or until air filtration removes them. This is why you can never fully dust a room. The tiniest particles are invisible, unsettleable, and everywhere. There's something almost philosophical about this. The same molecular motion that proves atoms are real is also the reason your house can never truly be clean. The same physics that reveals the structure of matter makes your allergies worse. Nature does not separate the beautiful from the inconvenient. Now let me take you somewhere unexpected, because I told you at the beginning that some of your dust came from space, and I wasn't kidding. Every day, somewhere between 5 and 100 tons of extraterrestrial material falls on the Earth. Most of it is extraordinarily small, particles less than a millimeter across, shed from comets and asteroids as they orbit the Sun. These micrometeorites enter our atmosphere at tremendous speeds, tens of kilometers per second. The smallest ones slow down high in the atmosphere without melting, like tiny parachutes breaking against the thin upper air. They drift down through the stratosphere, through the clouds, through the air above your city, and they land on your roof, on your car, on the sidewalk in front of your house. A scientist named John Larsen spent years collecting dust from the rooftops and gutters of Oslo, Norway, searching for these particles. He found them. Under an electron microscope, they're beautiful. Little spheres of melted rock and metal, some with crystalline structures from the extreme heating during atmospheric entry. They contain iron oxides, silicate minerals, and sometimes organic molecules. They carry the chemical fingerprints of comets that formed 4.5 billion years ago when the solar system was young. Before Larsen's work, the scientific consensus said it was basically impossible to find micrometeorites in populated areas. Too much terrestrial contamination, too many look-alike particles from human industry. People had found them in Antarctic snow and in deep-sea sediments where there's no urban dust to confuse things. But Larsen proved the experts wrong. He developed techniques to sort through ordinary rooftop gutter muck and pull out the cosmic grains. Many of them are magnetic because they contain iron, and many have a distinctive spherical shape from melting during their atmospheric plunge. He published his work, and now citizen scientists around the world collect micrometeorites from their own rooftops. You could do it yourself. The rate has been carefully measured by researchers who spent 20 years collecting micrometeorites from the pristine snow of Antarctica. The result, about 5,200 tons of cosmic dust reaches the Earth's surface every year. That's roughly 14 tons a day. 80% of it comes from comets of the Jupiter family, comets that originate in the Kuiper belt beyond Neptune. Now, the fraction of cosmic dust in your household dust is extremely small, vanishingly small, compared to the textile fibers and soil particles, but it's there. Mixed in with the lint from your dryer and the pollen from the oak tree outside, there are particles that have traveled across the solar system. You dust your bookshelf, and you wipe away a few atoms that last saw daylight near the orbit of Jupiter. I find that staggering. Not because it matters practically, it doesn't change your cleaning routine, but because it changes the way you think about what dust is. Dust is not one thing, it's everything. It's your skin and your cat's skin and your couch fabric and the dirt from the park and the chemicals from your mattress and the pollen from a tree a mile away and the fecal pellets of creatures you'll never see and tiny rocks from the cold depths of space. It's a sample of everything that exists around you, sifted through the air and deposited on your surfaces. And I want to push this further because there's a deeper physics lesson here about why dust exists at all. Everything breaks down, everything sheds. This is the second law of thermodynamics showing up in your living room. Entropy increases. Ordered structures, your skin, your clothing, your furniture, tend to lose bits of themselves over time. Molecules at the surface get knocked loose by friction, by heat, by chemical degradation, by mechanical stress. The universe has a preference for disorder, and dust is what disorder looks like when it piles up on your coffee table. Your couch is not going to spontaneously become more organized. It's going to gradually release fibers. The paint on your wall will slowly shed microscopic flakes. The rubber seal around your window will degrade and produce fine particles. Even the concrete in your foundation produces dust as it slowly weathers. Everything in your house is at a molecular level falling apart, slowly, imperceptibly, but constantly, and the debris of that falling apart is dust. Here's a number that drives us home. An average household generates and accumulates something on the order of 40 pounds of dust per year. 40 pounds. That's the weight of a medium-sized dog. Where does it all come from? From everything. From the slow molecular erosion of every material object in the house, combined with whatever drifts in through doors and windows and ventilation ducts. And the rate is not constant. Cooking generates particles. Candles generate particles. Burning incense, smoking tobacco, frying food in oil, all of these produce fine particulate matter that becomes part of your dust. Every time you fry an egg, you are creating PM 2.5 particles. The oil aerosol from the pan rises into the air, disperses through the kitchen, and eventually settles on surfaces along with all the other dust. Your breakfast contributes to the geology of your house. From the perspective of thermodynamics, your house is an entropy factory. You bring in ordered materials, furniture, food, clothing, and those materials gradually break down into smaller and less organized pieces. You eat food and shed skin, you wear clothes and shed fibers. You walk on floors and stir up mineral grains. The second law guarantees it. As long as your home exists at a temperature above absolute zero, which is always, the molecules in everything you own have thermal energy, and that thermal energy drives degradation. The only reason your house doesn't fill up completely with dust is that you fight back. You sweep, you vacuum, you wipe, you run air filters. You're an anti-entropy machine, temporarily pushing disorder out the door, knowing full well it will creep back in. It always does. There's a medical dimension too that I think is worth mentioning because it connects the physics and chemistry of dust to real consequences for real people. When environmental scientists sample household dust, particularly the fine fraction below 10 micrometers, they find a chemical cocktail that is genuinely alarming. Flame retardants from furniture, foam, and electronics. Plasticizers from vinyl flooring and food packaging. Heavy metals including lead, zinc, cadmium, and chromium from soil tracked in from outdoors. Pesticides from lawn treatments and pest control. Polychlorinated biphenyls, which were banned decades ago but persist in old building materials. And something the researchers call nonyl phenol ethoxylates, which are breakdown products of common detergents. Children are especially exposed because children crawl on floors, put their hands in their mouths, and play close to carpet level where dust concentrations are highest. A crawling infant breathes air from a zone that is 6 to 12 inches above the floor, precisely the zone where resuspended dust particles are most concentrated. An adult standing upright breathes air from 5 feet up, where the particle concentration is lower, so a baby in the same room as an adult is getting a much heavier dose of whatever is in the dust. Researchers at the University of California, Berkeley have been studying whether exposure to certain chemicals in dust might be linked to childhood leukemia. The data suggest that homes of children diagnosed with acute lymphoblastic leukemia tended to have higher levels of specific contaminants in their dust compared to control homes. I want to be clear that this is correlation, not proven causation. The study's controlled for income and other factors, but the mechanism is not yet established. Still, it's the kind of finding that makes you take dust seriously as a health question, not just a housekeeping nuisance. And there's an aspect of this that connects to how dust behaves physically. Smaller particles are more dangerous than larger ones, not just because they penetrate deeper into the lungs, but because they have more surface area relative to their mass. A 1 micrometer particle has 1,000 times more surface area per gram than a 1 millimeter particle. And since the toxic chemicals absorb onto the surface of particles, this means that the smallest dust particles carry the highest concentration of contaminants per unit mass. The particles you can't see, the ones that float forever, are the most chemically loaded. Physics and chemistry conspire here in a way that is elegant and deeply unfortunate. There's also the question of what happens when you clean. Vacuuming stirs up dust before it collects it. Sweeping is worse. Dry sweeping a floor can increase the airborne particle count in a room by a factor of 5 or more. It takes time for those particles to settle again. The ironic result is that the act of cleaning temporarily makes the air more polluted, not less. This is why air quality scientists recommend wet mopping and high-efficiency particulate air, or HEPA, filtration and vacuum cleaners. You want to trap the particles, not just redistribute them. The problem is made worse by a feature of modern construction that seems like it should be a good thing. Modern homes are sealed tighter than older ones. Better insulation, better weather stripping, less drafty windows. This is great for energy efficiency, but it also means less air exchange with the outside. And that means chemicals released indoors don't get diluted as quickly. They build up, they settle on dust, and the dust, as I said, acts like a sponge. It accumulates these compounds over months and years. Even regular cleaning can't get it all, because the finest particles work their way deep into carpet fibers and crevices where your vacuum can't reach. So we end up in a situation where the materials we choose for comfort and safety, flame-resistant furniture, stain-resistant carpets, non-stick cookware coatings, these same materials release chemicals that accumulate in dust and become a root of chronic low-level exposure. The engineering meant to protect you from fire ends up creating a different kind of risk. This is not an argument against flame retardants necessarily. It's an observation about how interconnected everything is, and how the physics of particles and surfaces creates consequences that nobody quite predicted. I think about the ancient world sometimes when I consider dust. Before synthetic chemistry, before plastics and flame retardants and non-stick coatings, household dust was simpler. It was dirt, ash from the hearth, fibers from wool and linen, grain chaff, animal hair and skin. A Roman household would have had dust too, but it would have been free of the 300 or more synthetic chemicals that modern researchers find. The physics was the same, particles settling, light scattering, Brownian motion, all of it. But the chemistry was entirely different. Our dust is a product of the industrial age. It carries the fingerprints of our technology in a way that would have been unimaginable a century ago. Archaeologists know this, by the way. They analyze ancient dust layers in caves and ruins to understand what people ate, what they burned, what animals they kept, how they lived. Dust preserves a record. A layer of dust in a Bronze Age dwelling tells you about diet and fuel and livestock. A layer of dust in your apartment tells you about polyester and polybrominated diphenyl ethers. The medium is the same. The message has changed. Let me circle back to where we started. You were told that the dust in your house is mostly dead skin, and I've now told you that it isn't. But I want to be honest about something. The exact composition of your dust depends on your specific home. A house with pets will have more dander. A house near a busy road will have more combustion particles and tire rubber fragments. A house in the desert will have more mineral dust. A house with old carpeting will have more fiber fragments. The point is not that there is one true composition of dust. The point is that the old simple story, the "it's mostly dead skin" story, was never based on careful measurement. It was an assumption that escaped into the wild and bred. And this is a pattern I see over and over in science. Somebody makes a rough estimate, somebody else repeats it, A journalist picks it up, a textbook includes it, and suddenly it's a fact, hardened by repetition, unchallengeable. Nobody goes back and checks. When you finally do check, you find out the world is more complicated than the shortcut suggested. That's the whole game, really. That's what physics is. You start with what everybody thinks they know, and then you go and look, and what you find is always more interesting than what you assumed. Always, without exception, the universe does not do boring. It does weird and complicated and subtle, and it disguises these things as ordinary, so that most people walk right past them. Dust is ordinary. Dust is the most ordinary thing in the world. You see it every day. You wipe it away without thinking. And yet in that thin gray film is a record of your life, your habits, your materials, your air. In it is proof that atoms exist. In it is evidence of ancient comets that last past the sun before human beings walked the earth. In it is the slow ticking clock of entropy, the thermodynamic destiny of every ordered structure to eventually come apart. Let me tell you one more thing before I go. There's something called Stokes' law, which describes how fast a spherical particle settles through a fluid. It was worked out by George Gabriel Stokes in the middle of the 19th century, and it's a thing of simplicity. The settling speed depends on three things: the size of the particle, the density of the particle, minus the density of the fluid, and the viscosity of the fluid. That's it. 3 inputs, 1 answer. And the dependence on size is dramatic. The settling speed goes as the square of the particle's diameter. Double the size of a particle, it falls 4 times faster. Halve the size, it falls 4 times slower. This is why sand falls fast and dust falls slow, and the smallest particles barely fall at all. Let me put some numbers on this so you can feel it. A particle that is 100 micrometers across, about the width of a human hair, settles through still air at roughly 25 centimeters per second. That's about 10 inches per second. It falls like a very slow raindrop. You'd notice it. A particle that is 10 micrometers across, 1/10 that diameter, settles at about 1/4 of a centimeter per second. That's 1/10 of an inch per second. It would take several minutes to fall from ceiling to floor in a typical room. You might see it barely in a sunbeam, drifting gently downward. A particle that is 1 micrometer across, about 3 micrometers per hour. 3 micrometers per hour. It would take days to fall from the ceiling to the floor if the air were perfectly still, and the air in your house is never perfectly still. Every footstep, every opening of a door, every convection current from a warm body or a light bulb stirs the air enough to keep these particles aloft indefinitely. But Stokes' law assumes the particle is in a smooth, continuous fluid. For very small particles, smaller than the average distance between air molecules, that assumption breaks down. The air is no longer a smooth medium, it's grainy. It's lumpy. The particle is small enough that it fits between the gaps in the molecular crowd, and the rules change. There's a correction factor called the Cunningham slip correction that accounts for this, and it tells you that the very tiniest particles fall even more slowly than Stokes would predict. This is a place where the graininess of nature shows up in your living room. The fact that air is made of discrete molecules, not a smooth continuum, affects how fast your dust settles. You can literally see the consequences of the atomic hypothesis in how long it takes particles to fall. A continuous fluid would pull them down more efficiently. But a molecular fluid lets them slip through. I think about this every time I see dust floating in a sunbeam. Each particle suspended in that golden shaft of light is telling you something about the molecular structure of the air it's drifting through. It's telling you about atoms. It's telling you about Brownian kicks and thermal energy and the balance between gravity and molecular chaos. And it's carrying with it a cargo of fibers and minerals and chemicals and perhaps a micrometeorite or two, a tiny library of information about where it's been and what it's touched. You can't look at dust the same way after you understand this. And you just can't. I used to think dust was what happened when things got dirty. Now I think dust is what happens when the universe operates normally. Dust is the default state. Cleanliness is the aberration. Organization is the temporary exception. Dust is the rule. And you know, there's a cosmic version of this too. The space between stars is full of dust. Not household dust, obviously, but tiny grains of silicates and carbon compounds and ice, drifting in the vast spaces between the stars. These interstellar dust grains are what block the light of distant galaxies and make nebula glow. They are also the raw material from which planets form. Every solid object in the solar system, including the Earth, including you, was once interstellar dust. You are dust that became organized, temporarily. That's not a metaphor, it's chemistry. The carbon in your body was forged inside a star, blown out into space when the star died, collected into dust grains, gathered into a disk around a new young star called the Sun, clumped together with other grains, built up into pebbles and rocks and boulders and planetesimals, and finally a planet. And here you are, a configuration of former dust that is conscious and reading about dust and shedding skin cells that will become dust again. The cycle doesn't stop. Your dust will eventually wash into the soil, weather into minerals, get swept into the atmosphere, and join the planetary dust cycle that's been running for 4.5 billion years. Some of your dust will end up in the ocean, some of it will end up in glaciers. A vanishingly tiny amount might eventually get launched into space by a meteor impact and float among the stars. That last one is unlikely for any given atom, but given enough time and enough atoms, the math says some of yours will make the trip. There's a wonderful irony in the fact that people spend enormous amounts of time and money fighting dust, sweeping it, and vacuuming it, and filtering it, and wiping it, and all along the dust was trying to teach them physics. Every time you dust a shelf, you're collecting a sample of the atmosphere, the materials in your home, and the history of your region's geology. You just throw it away. So here is what I want to leave you with. Go home. Find a sunbeam. Watch the dust. Don't wipe it away. Watch it. Watch the particles float and jiggle and drift. Remember that they're being kicked by invisible molecules. Remember that some of them are fabric threads from your own clothing. Remember that some of them carry flame retardants from your couch. Remember that a tiny, tiny fraction of them fell from space. And ask yourself, if something this ordinary is this complicated, what else are you walking past every day without noticing? That's the real lesson. Not about dust specifically, but about the habit of looking. The habit of not accepting the first easy explanation. The habit of going back and checking. Because nature rewards the people who check. But it always has a better story than the one we made up. I had a colleague once who used to say that the job of a physicist is to be professionally dissatisfied with easy answers. I like that. Easy answers are comfortable. They save time. But they cost you the universe. Every time you accept the easy version, you close a door. Behind every closed door is a room full of surprises. Dust is what's behind the door marked boring. And it's not boring at all. So do me a favor. Next time you pick up a dust cloth, pause for just 1 second. Think about what you're holding. Textile fibers from 3 continents. Mineral grains older than any civilization. Chemical traces of the Industrial Revolution. Proteins processed through the digestive tracts of arachnids. Pollen from a tree that might be half a mile away. And somewhere in there a few atoms that last saw daylight as part of a comet sailing past Jupiter. Tell me this. After what you've heard today, what do you think is the most surprising thing about the dust in your own home?